Welcome everybody to the second session of the first day of the Maryland Robotics Center Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series. This is part of the University of Maryland and Microsoft Robotics Diversity Initiative and is sponsored by Microsoft DC Metro Engineering Site. You can find all of our talks online at robotics.umd.edu/futureleaders. So today in this session, we are very lucky to be joined by Jana Pavlasek. And Jana is a PhD candidate in the robotics department at the University of Michigan. She is advised by Professor Chad Jenkins. Her research interests include robotic perception and planning under uncertainty in challenging and real-world environments. Particularly, her work focuses on scalable distributed inference algorithms, for example, including perception in clutter and multi-robot coordination. Developer and instructor for a course. She is also a developer and instructor for a core course on introductory robotics for the robotics undergraduate degree at the University of Michigan, which has been taught at several other institutions. So as part of distributed teaching initiative, other institutions have also taught this course that she's helped to develop. Prior to her PhD, she received a bachelor's degree in honors electrical engineering at McGill University, and she is a recipient of the NSERC postgraduate scholarship, and she also interned at NVIDIA Research. So please help us welcome Jana Pavlasek.
Hi, everybody. Thank you so much for having me today. I am going to be talking to you a little about my work on distributed inference for multi-robot coordination. But before I get started on that, I wanted to tell you a little bit about my first robot. So I went to McGill University to do my undergrad. That's in Montreal, Canada. And in my first year, I joined this design team where we built these underwater autonomous vehicles to participate in the RoboSub design competition, which is in beautiful San Diego. So this is me in my very first year doing this competition. And I learned a whole bunch of stuff doing this. One of the really key things I learned, though, was that underwater robots are really hard. So there's not a whole lot of, you often can't communicate with your robots. You need these really reliable autonomy algorithms. There's limited visibility in terms of, you can see the vision sensors, and there aren't a whole lot of sensors there's only a couple options that work well underwater. And then of course it's underwater. So you have to make sure that all of your electronics are constantly safe from that. So this is me again, having graduated up to being in charge of running these software runs by the pool. And so I started, when I was doing this design team, I really loved doing it. I thought it was really cool. I thought that I might want to do this as a career. And I was really lucky to get my dream internship at the Auto Motors division of ClearPath Robotics. I spent 2 summers there in my undergrad, and they build these big warehouse automation robots. And I was super excited to be there. But I was kind of thinking in the back of my mind, coming from this undergrad design team, these robots don't even go underwater. I'm not really sure what all these people with PhDs are doing working on these algorithms. But it turns out that actually this problem is a really hard problem. There's uncertain sensor data, there's humans in the environment, there's other robots to coordinate with. And so these algorithms need to be pretty reliable, even though you have these well-structured autonomy or warehouse type of environments. And so actually it turns out that this is a really challenging problem. And it kind of encouraged me to keep going with my robotics journey. And I started my PhD at the University of Michigan back in 2018. And I was really excited to work on these problems in robotic manipulation in these really challenging environments. So no green screens, no nicely set up environments that are kind of doomed to succeed, but we were dealing with these cluttered environments with a variety of different objects. And when you're dealing with these environments, there's a lot of uncertainty in your perception and your planning because of clutter and partial observability in the environments and sensor noise. And then these environments are very diverse. and unstructured. They can be dynamic. You saw a person come in at the beginning of this, especially if you have other agents. And so I've gotten to work on a couple of different applications in robotics, and it turns out that there's a lot of similarities in terms of the types of challenges that come up in robotic algorithms as they're applied to assistive home robotics, industrial automation, and robots out in the real world doing environmental monitoring, and also in education robotics as well. But I want to kind of zoom in on this assistive robotics application to start with, to kind of introduce some of the things, the projects that I want to talk to you about today. So if you have a robot that you want to do some assistive task for you in the home, like an assembly or maintenance task that might involve some hand tools, the robot first needs to actually be able to perceive those objects in order to figure out how to pick them up and how to use them. And that's can be really difficult if you have a scene like this where there are lots of occlusions or clutter and you don't necessarily have full observability. And then you also in this scene, there are articulated models and there can be kind of arbitrary different objects. And you can get these more complicated object models that you have to deal with. And if you have solved this perception problem, then the planning problem has the same kind of dimensions of complexity, because there's not one unique way to grasp an object in terms of what path you take to get to it and which actual pose you choose. And then you might have dynamic scenes which move around, which include other robots, and the multi-robot problem I'll be talking about in a little bit, or other agents or people in the environment. And of course, these dimensions of the perception and planning problem interact with each other, creating a problem that is complex and high dimensional, where there are multiple different solutions and a very diverse solution space. So what I focus on in my work is how can teams of robots operate reliably in these unstructured and dynamic environments. And the case I kind of want to make is that we need good models of uncertainty in order for robots to get this nice, reliable operation. And so the title of my talk has to do with distributed inference. And what I mean by that is that we can, instead of solving one big, very hard, high-dimensional inference problem, we can solve a bunch of smaller inference problems in parallel. And we can kind of pass messages between them in order to solve them. And we can apply this to different types of robotics applications that I will talk about. And I have gotten to work on a whole bunch of cool projects during my PhD and with a whole bunch of cool people, but I'm mostly just going to talk about these two today, about how we can apply these distributed inference techniques to articulated pose estimation and multi-robot coordination. So these are going to be the two parts of my talk today. So first of all, I wanted to tell you about the first project that I did in my PhD, which was about pose estimation of articulated objects, where we wanted to recognize and localize the pose of hand tools in order for robots to do some sort of task. And we wanted to be able to deal with these kind of cluttered, unstructured scenes. And so what we wanted to do is we were using the robot's camera, so it's RGB and it's depth observation, and we wanted to localize the 6 degree of freedom pose of the object, so the orientation, 3 degree of freedom orientation, 3 degree of freedom position, and then we're dealing with articulated objects when we're dealing with hand tools, so there's additional degrees of freedom from the articulation axis as well. And so our insight to this is a high dimensional problem, especially when you add articulations into it. And so what if we looked at this as a part space problem and used distributed inference? So we represent the tool as what we call a Markov random field, which is just an undirected probabilistic model where our nodes are poses of the object and edges are geometric relationships between the object that we know from the model of the tool. And if we can express our model this way, and we also assume that we've got some sensor observations. So in our case, the RGBD data from the camera, we can write down the joint distribution of the whole object, all of the different parts, as this product of two factors. So we can define a pairwise potential, which is going to, in this case, define the represent the geometric relationships in our articulated object structure. And then the unary potential is going to represent the compatibility of a pose with the observation that we have from the robot's camera. And our insight here was that what we wanted to do was to leverage both data-driven techniques, deep learning techniques, as well as probabilistic inference in order to get a method that has the strengths of both. So our pairwise potential allows us to integrate known prior information from the known geometry of an object. And we used a deep learned likelihood model based on a convolutional neural network, which let us do fast estimation, and we don't have to hard code any kind of complex likelihoods. And we use an algorithm called belief propagation to kind of fuse these two together and get a belief over the pose of our objects, which let us be robust to different environments. And so our learned likelihood, we use a convolutional neural network to get a heat map over the object over the image for the different object parts. And we use that we formulate that as a learned likelihood that we can use within our belief propagation method in order to get these, and we can combine that learned likelihood alongside our geometric model in order to get these a belief over our object poses. And from that belief, we use a particle-based belief. So that's a really flexible belief distribution that lets us represent arbitrarily complex distributions. We can draw an estimate from that belief in order to get our pose estimate. And what we were really interested in was how well this would do in clutter, where our deep learned likelihood is going to get potentially limited information from the sensor data because of occlusions. And we were able to recover this information by fusing our learned likelihood along with our geometric model through belief propagation. And so we're really excited about that. And since then, we've done some extensions about this work. We've looked a little bit into using implicit models like NeRFs in order to have a more flexible learned likelihood representation. And we've also looked at the manipulation side of things. How can this parts-based model be used to accomplish a robotic task by thinking about the affordances of object parts. But one of the things that what I was really interested in about this was this kind of distributed inference model that we had created, and its ability to lend robustness in these really high-dimensional, complex robotic problems. And we started to think in my lab a little bit about multi-robot coordination and wondering whether we could apply some of those same techniques in order to solve that problem too. And so that kind of leads me into the second part of my talk today, where I wanted to tell you about our more recent work on distributed multi-robot coordination. So in this project, we're basically considering how to control a swarm of robots. And so one of the approaches to do this is if we have full observability of our swarm, we can perform optimization over all of the actions of our robots and come up with one solution for the whole swarm. That only works if you can actually communicate with all of your robots. So in certain outdoor environments, that'll be challenging. And as you get larger and larger swarms, this problem becomes harder and harder to solve. It doesn't necessarily scale super well. So the other approach is to do decentralized control, where each robot has a controller on board, communicates with its neighbors, and just selects the best action for itself based on its own objectives and the group information that gets shared. And this is going to scale and a little bit better and has our nice property of distributed inference, where we can factor the problem into lots of smaller ones. And there's lots of people have been looking at these decentralized planning algorithms for a while. There's lots of really good algorithms, but they're really prone to a problem called deadlock. So you can see this is one of the kind of really good state-of-the-art algorithms on this, but if you give it a little bit of a couple constraints, like, a bit of a collision radius, it will it will get stuck a little bit easily, even in a smaller swarm. And we actually took this algorithm and we put it on this little swarm of real robots that we have with really noisy action models and noisy localization. These are actually little robots that we use for teaching that just have Raspberry Pis on them. And you can see that under real world uncertainty, the algorithm gets stuck and fails pretty often. And it also gets stuck in local minima more often. And we see a lot of these deadlock cases, even though we only have 3 robots. So we wanted to have an algorithm that solves this problem a little bit better. So I like to model problems probabilistically to account for uncertainty. So we thought we would model this multi-robot coordination problem as a Markov random field again. So now each of our nodes is a robot trajectory, and our edges represent robots that are within communication range of each other. And we are going to apply belief propagation just like we did before, which allows us to pass messages through the whole graph, which is a nice extra feature compared to algorithms where mostly they communicate with local neighbors. And in this way, it's kind of the same as our perception problem that we did before. And so to look at how exactly we formulate that, I want to jump to a single robot planning problem and just talk a little bit about how we actually think about planning as an inference problem. And so instead of just finding one single trajectory, we want to infer a distribution of trajectories so that we can consider multiple possible paths. And if you have obstacles or if you have lots of robots like we will have, you have a very multiple solution modes, and inference is very challenging in these cases. So often we'd use, if we use particle-based algorithm again, it's very prone to mode collapse. And so we got interested in this method called Stein Variational Inference, which is something I started looking at while I was working at NVIDIA. And compared to sampling-based methods, using Stein relies on gradient-based updates of the particles, and you can get these really nice multimodal distributions a lot more easily. And this was first proposed as a Coral paper back in 2020. We have a Coral paper from just this past year about how to scale Stein to work with uncertain goal sets. And we wanted to try to apply Stein variational inference to our multi-robot coordination problem, which we want to represent as a graph. So we actually introduced a new algorithm, which is called Stein Variational Belief Propagation. And so it represents distributions nonparametrically as particles. And it can do inference on a graph using signs. So we're combining the sign solver with the belief propagation algorithm. And we applied this algorithm to our multi-robot MPC problem, which is super high dimensional and challenging. And we can see that we get these really cool, smooth paths that by considering lots of different options can kind of get out of local minima and deadlock scenarios much better than our deterministic decentralized baseline algorithm. And we can get these kind of cool, smooth paths. And so we were really excited about how this worked in the simulated examples we were trying. And we wanted to see how it worked on real robots. So we took these robots that we develop at Michigan. They're called these MBOT robots. We often use them in teaching, but they're a really nice platform to see whether we can take this algorithm. We're actually using model predictive control, which is a pretty computationally expensive algorithm, and run it on something so lightweight as a Raspberry Pi with lots of action and localization noise. And we got pretty exciting results. We were able to this worked pretty well out of the box, even without necessarily explicitly modeling our uncertainty distributions. We were able to be pretty robust to all these different cases. And so that's a little bit about a quick brief overview of our distributed multi-robot coordination work. And so I wanted to kind of end in the last couple of minutes that we have with a little bit about what I think the takeaways of the work that I've talked a little bit about today is. And I think that the big question that I think about a lot is what is the best inductive bias for robotics problems in perception and planning. And so what I mean to tell you a little bit about, to explain what I mean about inductive bias, I really like this example, which is if we look at a heliocentric, or like a model of our solar system where the Earth, all the planets are going around the sun, which is what you see on the left, versus a model of our solar system where all the planets are revolving around the Earth. These actually turn out to be mathematically equivalent models. They are both correct models, but obviously the model where all of our planets go around the sun is a lot simpler, a lot easier to formulate, and easier to model. And we have gotten a lot farther by modeling it this way, in terms of that work. So that's kind of the importance of using the correct inductive bias. And so I think we should think more about what the best inductive bias is for robotics. In my work so far, I've looked at distributed inference and kind of graphical models, and representations of uncertainty, especially ones that can scale to the type of complex problems like nonparametric models. And I think that by combining these with kind of there's this really interesting new direction of work about differentiable probabilistic models, where we can kind of use all of the tools that we get from data-driven models in combination with probabilistic inference, to kind of scale these even farther to new applications. And so I think there's a lot of interesting work to do in this domain. So yeah, with that, if you want to learn any more about the work that I do, you can check out my website, and I have links to the papers that I talked a little bit about and other work I've done. I also teach a course at the University of Michigan that we also teach at a couple of other universities, which I didn't have a lot of time to talk about today, but you can learn more about that as well, and learn more about these little robots that we used in the multi-robot coordination problem. And so with that, I wanted to thank my collaborators and funders that contributed to all these projects that I talked about today that I couldn't have done without them. And yeah, thank you. I'm happy to take any questions.
Yay, thank you. You have to deal with only me clapping up here on behalf of myself and the entire list of attendees. So we have a question from the audience. What about axis? This is in regards to the first half of your talk. So what about the axis of the object? How do we parameterize that?
I'm not sure what do we mean by the axis of the object. I think maybe you mean the articulation degree of freedom, which actually, so when we model the problem as a parts-based problem, we're kind of inherently modeling the articulation as well. Like from the pose, we can get the articulation degree of freedom back as well. So that's kind of how, instead of explicitly modeling it as just a higher dimensional problem, the parts-based approach kind of encompasses that as well. I hope that was what you meant by your question.
The question asker says,
okay.
kind of in terms of to pick up a hammer, for example, is
Oh,
it
yeah.
pick up sideways rather than vertically,
Oh, yeah. Yeah, so I think right. That's a I see what you mean. So when you're talking about that's kind of like an affordance-based grasp, I think is what we would call that, where there's actually a best way to pick up the object based on what you actually want to do with it and how you actually want to use it. So we didn't explicitly think about what the grasp pose would be when we were working in the project that I talked about, but I did mention that other work about affordance coordinate frames, where later work we tried to think more about, and like some of my lab mates tried to think more about how we could grab an object based on what our actual goal was. And that's definitely a really interesting and open area of work.
Right. Okay. So another question from the audience is, someone is wondering if the localization method you presented can be used for real-time tracking of moving objects in a cluttered space. For example, how much computation time does the model require for such real-time applications?
Yeah, that is always a good That's always a hard question to answer when in a research lab. A lot of it just depends on how well I wrote my code, you know. But so I think we were at about like a couple seconds to localize each object. If you paid me the amount that you pay research engineers at a company to do that, I could do it much faster than that. But there's so I think you could probably get it, maybe not real time, but a little bit faster. Definitely the message passing approach when we're talking about belief propagation does take some time. But I think that there's like people are writing algorithms to do these auto differentiation and likelihood evaluations kind of faster and faster. So I think that that's we can actually there's some work that's been doing these pretty high dimensional problems in pretty real time for robotics. So yeah, it's a good question though. Important question for robotics.
Thanks for the response. I have a question personally, and you're free to say this is an unfair question, but it looked like in your talk, some of the objects that you presented looked like they were getting at something that you didn't really talk about in the talk today. So the clamp is a good example where it may be in different configurations based on how spaced out the two like ends of the clamp are ever. And so that will change the relationship between the states, but it's still the same object. And I guess like the pliers could also kind of open up or close, which is different than like a hammer, which like doesn't have a joint articulation or some other way of putting that. So does the method that you presented the first half of the talk consider this stuff, or are they kind of baked into those specific configurations?
No, yeah, we absolutely consider the articulation. So when we write we actually, our geometric constraints in those pairwise priors that I talked about are actually using the URDF model. So it will allow but it will also infer the configuration of the articulation kind of implicitly while finding the pose. So it works explicitly with articulated objects. Yeah.
Okay, wonderful. That's great. It seemed like a reasonable thing, but I wasn't quite sure. Also, how sensitive is the model to different view angle of the camera and or distance of the camera?
Yeah, well, definitely we're looking at more like tabletop views. So it's kind of as sensitive as I guess it's as sensitive as your camera is, and as your depth camera is. Depth cameras often have a more narrow field of view. So we were mostly looking at a tabletop type of view, but it's not necessarily restricted. I guess, yeah, that would depend on your camera. But the other part of your question was about viewpoints, which I think would mostly affect the occlusion. So obviously with more occlusions, if you're looking at it like completely from the side and you can only see one part, that's going to be a lot harder to infer the position. So it would be sensitive to viewpoint in how it's related to occlusions and your ability to actually perceive the different parts of the object.
Thank you very much. Well, thank you again for speaking at our seminar series, Jana Pavlasek. And all of these talks are online. Anybody that wants to see this or any other talk from this series can go to robotics.umd.edu/future leaders. And I'd like to thank you again for coming to speak with us.